Hello, everyone. Welcome to our talk, Do Vision Language Pre-trained Models Learn Composable Primitive Concepts? Recently, there are lots of vision language models reaching impressive performance on multi-model tasks and even zero-shot recognition tasks. Many of them are trained with unlabeled pairs of images and captions from the internet. These unlabeled pairs of images and captions usually encode complex concepts, or say high-level concepts such as ripe golden pineapple or blue jay. And the models, as expected, learn to predict these complex concepts pretty well. However, it is unclear whether the models do such a good job by reasoning over the primitive concepts such as colors, shapes, texture of the object, or wing color of the bird. In our work, we care about whether these vision language pre-trained models can learn composable primitive concepts. We raise two sub-questions. First, do they learn primitive concepts? Second, do they learn the correlations between primitive concepts and the composite concepts? However, first, why do we care about primitive concepts? First of all, it is one of the preconditions for the model to reach compositional generalization. Just as the example I show here, because I understand color concept red and the general appearance of a banana, so I can name this object as red banana correctly, even though I have never seen such object before. Such understanding of primitive concepts is one of the preconditions for a model to reach compositional generalization. Also, it brings better interpretability and allows more interactions between the users and the models. For example, prior work used an intermediate bird attribute classifier and also a bird class classifier on top of this intermediate layer. If bird attributes are predicted incorrectly, users can manually correct the predictions such that the bird class classifier can still predict the correct bird class at the end. However, such models usually require expensive manual annotations of primitive concepts. Therefore, it would be great for vision language models to automatically learn primitive concepts. To investigate how well vision language pre-trained models learn primitive concepts, we propose compositional concept mapping framework. Our key motivation is that a mapping from primitives to composites can be obtained in data-driven fashion by simply learning linear classifiers, which we call as composition models. We hypothesize that one can reliably learn a composition model if there exists a good enough annotated dataset for primitives and composite concepts. However, in the more common situations, we don't usually have the primitive concept annotations. Therefore, we introduce our first component of CompMap, concept prompting, which will leverage a pre-trained vision language model to automatically annotate the primitive concepts on the fly via natural language prompting. Here, we show an image of a bird, and we will also have a predefined set of bird attributes, which are primitive concepts in this case. We fit each bird attribute into prompt template and pass this image and each prompt into a frozen pre-trained vision language model to predict concept activations, where each element corresponds to the alignment between the bird image and a bird attribute. Then we step into second component of CompMap, composition learning. We will train linear classifiers, which we name as composition models, to classify the composite concepts based on the predicted concept activations. We will use composition model as a proxy to reflect how well vision language pre-trained models learn primitive concepts. Before we introduce how we use composition models as the proxy, we would like to first introduce the metrics we use to quantify how well vision language models learn primitive concepts. We first introduce usefulness, which is the quantitative evaluation metrics on composite concept recognition tasks. Our interpretability metrics based on an assumption that a composition model trained with ground truth primitive concepts can reliably predict the corresponding composite concepts, which we call it as ground truth composition model. If a pre-trained vision and language models learn primitives well, their predicted primitives should allow us to learn a composition model that performs similarly to a ground truth composition model. For example, if we have a specific bird class, red-winged blackbird, and two types of concept activations, ground truth concept activations, which are binary, and also the concept activations predicted by a pre-trained vision and language model. As step A, we first train a ground truth composition model based on the ground truth concept activations. And then, as step B, we train another composition model based on the concept activations predicted by the vision and language model. During the inference time, we evaluate the model, or say we intervene the model with the ground truth concept activations. And we can see that the model will incorrectly predict the bird class because it incorrectly correlates the green background with the red-winged blackbird. Our interpretability metric is the performance gap between the learned ground truth composition model and the composition model learned from predicted concept activations. Thus, the lower the interpretability metric is, the more interpretable a composition model is, implying that this pre-trained vision language model learns primitive concepts better. In our experiments, we explore two data sets, MIT states and CUB. On MIT states, we evaluate the models with compositional zero-shot learning task. In this task, during the training, the model will be trained with composite concepts that cover a predefined set of primitive concepts. During the inference time, the model will be evaluated with some part of the seen and unseen composite concepts. On CUB datasets, the dataset comes with bird class and also the bird attributes. And the model needs to classify the bird class based on the bird attributes. We want to elaborate that a true composition model would look like a set operation. For example, on MIT states, it comes with attributes and objects. For example, for concept red, it can get represented as a one-hot vector, and same for the apple. If we concatenated these two one-hot vector together and get the two-hot vector, this two-hot vector can represent the composite concept red apple. Similarly for CUB, we can concatenate 28 such one-hot vector for each bird attribute category and get a 28 hot vector to represent each bird class. Our experiments cover the main dimension of vision and language models, including models with no fusion, early fusion, and late fusion. From now on, we will name the ground truth composition model that is learned from binary ground truth primitive concepts as Oracle Prim. We will first show the results evaluating the interpretability of learned primitive concepts. Using CUB, we evaluate the model using N-way K-shot fusion learning setting. And the full shot column here means that the models are trained with all the samples with all the classes. First, we show the results for Oracle Prim, which performs nearly perfectly, validating our hypothesis that a linear composition model can be learned from ground truth primitive concepts. Then, we show the results for the composition models learned from predicted concept activations from the vision language models. Then we intervene the model during the inference time, and we can see that the results are worse than the composition model, VL Prim, indicating that the learned primitives are not interpretable. At last, we combine the ground truth concept activations with the predicted concept activations by activating the ground truth primitive concepts in predicted concept activations. We can see that this partial intervention performs significantly better than full intervention, implying that the models are utilizing irrelevant primitive concepts to predict the composite concepts. Furthermore, we showcase the interpretability metrics over two data sets, MIT states and CUV. We can see that the performance gaps are significantly large. Therefore, we draw to the conclusion that the learned composition models are not interpretable, reflecting that the vision language models do not learn interpretable primitive concepts well. Later on, we carry out analysis over the learned weights of composition models. First, we carry out a qualitative analysis on CUV datasets for ClipPrint model. On each row, we showcase the results for a specific bird class, and the x-axis on each subplot corresponds to a different primitive concept. And the y-axis corresponds to the likelihood for primitive concepts get aligned with the bird class. The blue bars are the ground truth primitive concepts. As we can see here, ClipPrint models does not align the primitive concepts with the bird class correctly for most of the time. In order to better understand, we carry out quantitative analysis of the learned weights of ground truth composition model and the learned weights of compositions learned from concept activations predicted by CLIP. We measure the performance using accuracy, which will measure whether the most activated weights align with the ground truth primitive concepts. Here we have accuracy instance, when we treat each alignment as a single instance, and accuracy class, where a model needs to align all the primitive concepts correctly for a composite concept. Accuracy attribute and object are alignment accuracy on attribute category and object category in MIT states. We can see that ARPO-Prim can almost perfectly align the primitive concepts with the corresponding composite concepts. However, the learned weights of ClipPrim does not align correct primitives for the composite concepts for most of the time. Thus, ClipPrim model behaviors are different from a ground truth composition model. Next, we show the results on usefulness of composition models on MIT states. We measure the performance using area under curve, which is similar to accuracy. The higher the AUC is, the more accurate a model can predict the composite concepts. Seen and unseen are accuracy scores over seen and unseen concepts during inference. HM is the harmonic mean over seen accuracy and unseen accuracy. First, we show the results for prior works. We observe that even using just a pre-trained clip, it can already perform very competitively over the prior works. Furthermore, if we apply the vision language models with our comp map, the models can outperform all the prior works. Therefore, the learned primitive concepts are useful for image classification tasks. Last, we investigate whether the usefulness of concept activations comes from the primitive concept prompting or the powerful visual encoder of CLIP. First, we directly use the CLIP image embedding, and we observe that it performs better than ClipPrim, which we attribute this by the high dimensionality of a CLIP image embedding, comparing with the concept activations. Next, since concept prompting can be viewed as applying a projection matrix on the CLIP image embedding, we also consider two alternatives for the projection matrix used by ClipPrim. We explored a learned projection and a frozen random projection. As we can see here, ClipPrim only moderately outperforms the learned and random projection baselines, indicating that the usefulness mainly comes from the CLIP visual encoder and not from the primitive concept prompting. This wraps up our work. We proposed a two-step framework, comp map, to measure how well vision language pre-trained models learn primitive concepts in terms of interpretability and usefulness metrics. Based on our experiments, we observed that the learned composition models trained from predicted primitive concept activations from vision language models are not interpretable. However, the predicted primitives are useful for visual recognition tasks. In all, we believe there should be more research needed to improve vision language models' ability to capture primitive concepts. Thank you.